Okay, so the infamous permutations, combinations, and we're going to also talk about the binomial theorem. So permutations, combinations, and the binomial theorem. Okie dokie. And, there was this notation that we had for the number of sequences of size, binary sequences of size n with k ones. And that was nk. And we saw that this is equal to number of n-bit sequences with k ones. It's also equal to the number of, ways to choose k students from n to make a committee. Okay, now choosing k students from n to make a committee, that's a subset of the n students. Okay, and we say it's a subset because we don't care about the order in which the students are picked. So sometimes we'll call this a k subset. And this number nk also appeared, and this is why this is called n choose k. This number n choose k also appeared when we talked about goodie bags. So this guy is all over the place. Yet we don't have a formula for it yet. We're going to get a formula now with this interpretation as the number of ways to choose k students from n to make a committee. Okay, so imagine you have 4 students. So you have a set of 4 students, okay, which is, let me label the students 1, 2, 3, and 4. Okay, now remember when we considered the top 3 finishers in a group of 10 students. Okay, now when you consider the top 3 finishers in a group of 10 students, the order matters. So let's consider the top 2 finishers in a race with these 4 students. What are the possible arrangements for these top 2 finishers? Well, you could have 1, 2, you could have 1, 3, 1, 4, you can have 2, 1, 2, 3, 2, 4. We have 3, 1, 3, 2, 3, 4, and 4, 1, 4, 2, 4, 3. Basically, anyone can come in first, and then of the remaining 3, anyone can come in second. Okay, and so by the product rule, you have 4 times 3 ways in which to construct the top 2 finishes. Okay. If we were only interested in subsets of size 2, so we can call these the 2 permutations. The permutations of size 2. Okay, so permutation means order matters, the number of ways to construct, a sequence of length 2 from these objects. Okay, so those are called permutations. Now, if we don't care about the order, we're only interested in a subset of 2 students. Well, when you choose the first student and the second, that's the same as choosing the second student and the first. So these 2 would be the same. Okay, so if we listed out the subsets that we can form of size 2, we get 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. So there are only 6 subsets of size 2. There are 12 permutations of size 2. So there are 12 permutations of size 2, and there are 6 subsets of size 2. We can sometimes call these 2 subsets. And sometimes these are also called, there are 6 combinations from this original set of size 2. These are called combinations. So in permutations, the order matters. In combinations, the order does not matter. Now let's jump straight to full generality. Imagine the set had n students. So S equals 1, 2, 3, 4, all the way up to n. Okay. And we're interested in a k permutation. So we're interested in the top k finishers of a race. So top k finishers. Okay, so there are n ways to choose. So top k finishers means we're going to pick a student S1 who came first, S2 who came second, and all the way to SK who came in kth. Okay, so there are n ways to pick this student, n, because there are n students. But once you pick the winner, there are only n minus 1 ways to pick the second place student. And the product rule says n times n minus 1. Okay, and then the third guy times n minus 2. And then so on and so forth. Ultimately, you get to how many ways can the kth person be picked. And after when you're about to pick the kth person, k minus 1 people have already been picked. So you have n minus of k minus 1 availabilities for the student who came in kth, okay, because k minus 1 have been picked. So this is exactly equal to n This is equal to n times n minus 1 times n minus 2 times all the way times n minus k plus 1, okay, which is equal to n times n minus 1 times n minus 2 times all the way to n minus k plus 1 times n minus k, so I subtracted another 1, times n minus k minus 1, so I subtracted another 1, times all the way up to 1. So I added a whole bunch of terms in this product, so I had better divide by those terms. So divided by n minus k minus 1 all the way to 1. Okay. Now on the top I have constructed exactly n factorial, so this is n factorial, and on the bottom I've constructed exactly n minus k factorial. And this is interesting. So the number of top k finishes in a race with n students, okay, is exactly n factorial divided by n minus k factorial. Now, I'm going to show you another way to compute the number of top k finishes. Okay. Now, another way to compute the top k finishes is, so here is another way to compute the top k finishes. Step 1. Figure out who's in the group of top k finishes. So find the subset of students in the top k where order doesn't matter. So this is just a subset. So this is a order not mattering. So first step in deciding who is finishing in the top, or in deciding how the top k finish, is figure out who is in the top k. Okay, but this is exactly picking a subset of size k from my original n students. So this can be done in n choose k ways. Okay, that's the definition of n choose k. Okay, now that you've figured out who is in the top k, rank order them in order of first, second, third, fourth up to k. Now rank order them. So you've picked your k students, and now you need to rank order them 1, 2, 3, first, second, third, fourth, and so on up to k. Okay? But this also we know how to figure out the number of finishes among k students if they ran a race. There are k ways to pick this guy, then once you fix that, there are k minus 1 ways here, k minus 2, k minus 3, and all the way to 1. Okay? So the number of ways to rank order my k students, once I've identified who's in the top k, is exactly k factorial. And once I pick the k students and then rank order them for the order in which they finish, I've got exactly a way of constructing the top k finish. And by the product rule, the number of top k finishes constructed this way, okay, is equal to this, the number of ways to identify who's in the top k, okay. Think of that as the first step in the process, okay. And then by the product rule, you multiply the number of ways to decide who's in the process, who's in the top k. Once you pick those, how many ways can you order them? The product rule says, okay, that's k factorial. So you multiply the number of ways to pick who's in the top k by times the number of ways to choose the ordering after you fix the top k, which is k factorial. And once you pick the top k and then order them, you have exactly a top k finish. So the number of top k finishes that we have computed this way had better equal the number of top k finishes that we have computed this way. So what that means is that n choose k times k factorial must equal n factorial divided by n minus k factorial. Or, and I'm going to put it in a big box, n choose k is equal to n factorial divided by k factorial times n minus k factorial. I just divided both sides by k factorial. So I took this k factorial into the denominator. Let's box it. Fantastic. We now have a formula for n choose k. The number of ways to choose a k subset from an n element set is called the number of combinations of k from n. It is also the number of binary sequences of length n that have exactly k1s. And that formula appeared so many times that tells you how important this formula is. This formula for the number of n-bit binary sequences with k1s, the number of ways to pick a k subset from n, very important formulas. I'm going to erase everything, but I'm going to leave that formula here, and we're going to talk about the binomial theorem. Okay, binomial theorem.